Hello, welcome back to my two-episode series where I am explaining the Alcubierre work drive in as simple terms as I can get it. But I am Andrew, and the first episode of this two series was about like the general mechanics of the warp drive. And this second one is going to be about the problems and solutions for it. In the previous episode, while trying to explain the general mechanics, just as like a keepsake, I guess. I briefly mentioned the energy cost for the drive. That cost may be inaccurate due to fluctuations with speed, mass, warp bubble size, wall thickness, and other factors to account for when you're trying to calculate faster than light travel. I mean, it's not like that's some sort of like difficult task or anything. I don't know what you're talking about. The main issue with the Alcubierre drive is possibly and probably the most obvious, which is the amount of energy required for it. There are of course other issues such as how big it'd have to be, like the I guess general size for it, since there's it's going to be a long time till we can build something that massive, assuming it would be massive. Then, as well as that, coming up with a possible thing to actually produce that Alcubierre drive, like trying to reinvent the engine except on hard mode, more than hard mode actually. It's like trying to reinvent physics, I guess. But and then there are of course other issues with it, like the general research for it. Just literally anything you can think of, we probably need it, or at least need more of it. But more than any of that is the amount of energy required for it, which, according to Alcubierre's original estimates in his first research paper he published, or not, maybe not the first one, but his main one, which is called The Warp Drive Hyperfast Travel Within General Relativity, published May 1994. That calculation from him calculated that you would need about the energy mass of Jupiter, which the energy mass is just the energy you get for plugging the mass of something into the equation E equals mc squared. E is energy, m is mass, c is the speed of light. So like if you were to put, say, something with a mass of 1 kilogram into the equation, you would get E is equal to 1 times about 300 million squared, since the speed of light is like 299 million with change. So just make it a nice 300 million. Right. And the mass is in terms of kilograms, E is in terms of joules, and C is in speed of light in meters per second. But then for a quick energy reference, I guess, on how big these numbers are that we're going to need. In 2023, the total energy we generated was somewhere around 30,000 terawatt hours, which is about 10 to the 19 joules, according to Statista. That's a that's a pretty big number. That's one with a lot of zeros. And Miguel Alcubierre originally estimated that in his paper that Jupiter was like about the mass of something that we would need for the energy mass, but the total energy mass we'd need is, or with his original estimation, would be about 1.7 times 10 to the 46 joules, or in more word sense, like more size comparable sense, 17 quattordecillion joules, which is the 14 version of million. So it'd be like 100,000 million, billion, trillion, quadrillion, up to octillion, nonillion, decillion, undecillion, duodecillion, tridecillion, then quattordecillion. So that's a pretty big number. And that amount of energy is near impossible to obtain. And if that is the only solution, or I guess the minimum amount of energy required, FTL travel or Alcubierre Drive just will probably never become a reality. And if it does, it will be in the far future and will stay as sci-fi for significantly longer than anyone hearing this will be around for. But on a much brighter, more optimistic note, the research paper published by NASA called Warp Field Mechanics 101, which is a summary of the, I guess the paper itself was a summary of a project led by Dr. White in a division called Eagle Works. In that project, they revised and strengthened a couple of Alcubierre's original estimates, which one of them, thank goodness, is the energy requirement. In this research paper, which I heavily recommend you read through or look through if you're curious, is the energy requirement, or is that the energy requirement was brought down from about the energy mass of Jupiter to around the energy mass of Voyager 1. This amount of energy is significantly more capable and possible, coming in at around 6.49 times 10 to the 19 joules, which is like almost 2/3 of the total energy produced in 2023. So, pretty big number still. But on paper, this may sound possible if you're extremely optimistic, but uh, because we're already generating enough energy for this, but that's the energy of the entire planet. So we need to find a way to generate that much extra energy. So like, even then, we have to have like one organization generate that much, because unless all of humanity happens to band together in the hopes of fast and light travel, we probably will not be getting help from anyone else, because it's just too futuristic of technology to care about. But and not just the energy generation, but we'd also need to be able to store it. That storage is one of the more difficult parts of it. uh, energy can't really just energy definitely cannot just be stored in batteries, and it's just there's a reason it's described in terms of energy mass, but that's because it's not actual electric energy we need. It's like potential energy, I guess, like the fuel. Trying to describe it as fuel, since we still don't really completely know what fuel we'd be using for it or would use for it. But we'd have to store it in, I guess, quote unquote, store it in some sort of material or something. So we can't just use like gasoline. That ain't nearly good enough. No rocket fuel is good enough. Just nothing has a high enough mass to energy ratio, or I guess conversion ratio, but except for two materials or two types of matter that we know of or have at least thought of: exotic matter and antimatter. Currently, nobody really knows what exotic matter is, or mainly what it's like made of. That's because it's never been observed, produced, or really even proven to exist, since it's just a theoretical form of matter with abnormal properties such as like negative mass. And the other fuel option is the most feasible, since it's already been observed and proven to exist: antimatter. Antimatter is a form of matter that, instead of the atom having a positive nucleus, protons and neutrons, have negative orbitals called electrons. But that antimatter instead has a negative nucleus consisting of antiprotons and antineutrons, and a positive orbital made of protons. But it still has the same mass, electric charge, and magnetic movement of any ordinary matter of the same element as described by Britannica. Antimatter is very useful, yet dangerous in this scenario due to antimatter's very reactive nature. So it's trying to use like sodium or one of those fun reactive things in a submarine, if that's a decent comparison. Actually, it's not even close. it's it's not enough of a dangerous enough of a scenario. But the reason why antimatter is so difficult to handle is because it doesn't matter what it touches. If it touches oxygen, you're gone. If it touches anything, any ordinary matter, it goes through a scientific process called annihilation. And when something gets scientifically named something like an annihilation, you know it's bad. That's because the ordinary matter and the antimatter, since they're opposite charges, slam into each other, completely converting both of their matters into energy. With the equation equals mc squared. So if you were to have like matter, or I guess 1 kilogram of antimatter and 1 kilogram of normal matter, the two would, or that energy produced would be put into the equation. 1 plus 1 is 2 from the 2 kilograms of types of matter that were smashed together. So it would be the energy is equal to 2 times the speed of light squared. And that's the total energy that would have been just produced. But this makes antimatter unsurprisingly difficult to store. Because to store it, you have to trap it in some sort of way so that it doesn't come in contact with any matter, or else bye-bye antimatter and bye-bye your storage device. But to do this, so far we have come up with like field, like some sort of like magnetic field to store it, like trying to trap it in a vacuum. This, honestly, it's difficult, but it's possible, especially considering the fact that it's been done. That makes it easier to believe. But at CERN, I'm not sure if you know what that is, but it's like a massive research complex dedicated to researching particles. CERN got to hold antimatter or store antimatter for about 1,000 seconds, which is a little more than 16 minutes. But you might think, how on earth can we store antimatter? Because there's no way we have it. But that's where you're wrong. We've had antimatter for a long time now. I mean, it was in 2011 that the antimatter was stored in CERN. To create it, though, CERN uses a massive tube. I guess massive tube is an understatement. It's like the size of a major city. But the tube collides protons into each other at a little under the speed of light. I think it's somewhere around like probably about like 97, I think, percent the speed of light. But when those protons smash into each other, they create antiprotons alongside other particles, such like the God particle. But we don't talk about that here. This is about the Alcubierre Drive and its energy, not God particles or anything. You can search that up on YouTube if you want it. It's a good video. I've watched stuff about that. Pretty fun stuff. But that antimatter that's produced from that required such a high amount of energy to actually make the antimatter, from speeding up particles to near the speed of light. But even then, the amount of antimatter produced is so minuscule that we'd need to do that so many times, holding it consistently throughout, that it's just a massive hurdle. We'd have to find a way to mass produce antimatter if we really want to make Alcubierre Drive a reality, or at least semi-feasible. But even then, it's only really possible to be considered if the Eagleworth's recent calculations were in fact correct. Even, or if they are, then it's possible that the FTO travel isn't really that far in the future. Now, of course, extremely far, but not as far as you probably would think. Like, probably not in like a million. We'll probably have it in a million years. If they are correct, maybe in 1,000, maybe in 500. I don't know. Really depends on how much we want to put into it, and if it's even possible in the first place. But then, assuming we have the antimatter for it, how much would we need? I mean, we're trying to compare like bending space time to goofy type of matter that this might be the first time you've heard of described. But for an object, I guess for an energy mass of about 700 kilograms, the approximate weight of the Voyager 1, which is what EcoWorks calculated about, the equations they revise is about it. They said you'd need around like 700 kilograms of energy mass. You'd need about like 350 kilograms of antimatter and 350 kilograms of ordinary matter, because 50% antimatter, 50% not so antimatter. But not just that though, because you'd also need to make more than that, because it's not 100%. I guess it is 100% matter into energy, but we don't have 100% efficiency with energy. It's like, sure, it'll all be produced, but we won't be able to actually use 100% of it, since a lot of it is in photons. I believe I read somewhere that it was 70% that we can use, like max. Don't quote me on that. But then, I guess, even if you were to find a way to store and produce enough antimatter, and like enough to overcome the fact that you can only use probably like 70% of the antimatter, because the rest just gets turned on to, or turns into photons, you'd have to overcome, or I guess you'd have enough antimatter to overcome the biggest hurdle in bringing the theoretical drive into reality. But I mean, yeah, congratulations, you have the power to make a faster than light, probably, if if you're lucky. But I guess if you could go that route, make antimatter, or you could be fancy and discover a new type of a new type of matter just for an Alcubierre drive called exotic matter. Please discover. I would really like to learn about that. But I think antimatter is the easier route. I do believe that is all I can really explain about the energy requirement for the Alcubierre warp drive. Thanks for bearing with me while I probably pretty poorly explained the energy requirements for FTE, or for our FTL travel. I guess thanks for listening.